Okay. Let's break down Shannon entropy. Starting from the simplest intuition and gradually adding more technical detail. Level 1. The surprise factor, intuitive. Imagine you're watching the weather forecast. Scenario 1. The forecast says sunny tomorrow. You're not very surprised. Sunny days are pretty common where you live. Low surprise. Scenario 2. The forecast says blizzard tomorrow. Whoa. That's a big surprise. Blizzards are rare. High surprise. Shannon entropy, at its core, measures the average amount of surprise or uncertainty associated with a random event. The more unpredictable something is, the higher its entropy. Level 2. Probability and uncertainty, slightly more formal. Probability. The chance of something happening. E.g. Comma. The probability of flipping a fair coin and getting heads is 1/2 or 0. 5. Uncertainty. How unsure we are about what will happen. Entropy is high when there are many possible outcomes. Each outcome has a relatively equal probability of occurring. It's hard to guess what will happen. Entropy is low when there are few possible outcomes. One outcome is much more likely than the others. It's easy to guess what will happen. Example. Coin flip, fair coin. 2 outcomes, heads, tails, each with probability 0. 5. High entropy, relatively. Coin flip, biased coin. Heads has probability 0. 9. Tails has probability 0. 1. Low entropy, we're pretty sure it will be heads. Level 3. Information content and bits, introducing information theory. Think of entropy as measuring the amount of information you gain when you learn the outcome of an event. Low entropy event. You don't gain much information because you already had a good idea of what would happen. High entropy event. You gain a lot of information because the outcome was very uncertain. The unit of information is the bit. 1 bit represents the amount of information you get from an event with 2 equally likely outcomes, like a fair coin flip. Knowing the result of a fair coin flip gives you 1 bit of information. Level 4. The formula, mathematical definition. The Shannon entropy, denoted by h, of a discrete random variable x is defined as h, x, equals, Greek letter sigma p, x, log 2, p, x, where x is the random variable g, comma, the outcome of a coin flip, the weather tomorrow. X represents a possible value of the random variable g, comma, heads, tails, sunny, rainy. P, x, is the probability of the outcome x. Greek letter sigma means sum over all possible values of x. Log 2 is the base 2 logarithm. The base of the logarithm determines the units of entropy. Base 2 gives bits. Base e gives nats. Base 10 gives dits. Explanation of the formula. 1. P, x. The probability of a specific outcome. 2. Log 2, p, x. This part calculates the information content or surprise associated with that specific outcome. Notice that if p, x, is close to 1, very likely. Log 2, p, x, is close to 0, little surprise. If p, x, is close to 0, very unlikely. Log 2, p, x, is a large negative number, big surprise. 3. P, x, log 2, p, x. We multiply the probability of the outcome by its information content. This weights the surprise by how likely the outcome is. The negative sign makes the entropy positive, since logarithms of probabilities are negative. 4. Greek letter sigma. We sum this value over all possible outcomes. This gives us the average information content or surprise. Example, fair coin. P, heads, equals 0. 5. P, tails, equals 0. 5. H, coin, equals 0. 5 log 2, 0. 5, plus 0. 5 log 2, 0. 5. H, coin, equals 0. 5 minus 1 plus 0. 5 minus 1. H, coin, equals minus 0. 5 0. 5. H, coin, equals 1 bit. Level 5. Applications. Why is this useful? Shannon entropy is used in a wide variety of fields. Data compression. Entropy helps determine the theoretical limit of how much a piece of data can be compressed. Algorithms like Huffman coding use entropy to assign shorter codes to more frequent symbols. Machine learning. Decision trees. Entropy is used to choose the best features to split the data on, aiming to reduce uncertainty about the class labels. Information gain is a related concept. Feature selection. Entropy can help identify features that are most informative for a given task. Cryptography. Entropy is a measure of the randomness of a key. Higher entropy keys are harder to crack. Information theory. The foundation of digital communication, data storage, and signal processing. Genetics. Analyzing the diversity of genes in a population. Linguistics. Measuring the complexity of a language. Finance. Assessing the risk associated with investments. Level 6. Beyond the basics, for the curious. Conditional entropy. The entropy of a random variable given that you know the value of another random variable. H, yx, is the entropy of y given x. Cross entropy. A measure of the difference between two probability distributions. Often used as a loss function in machine learning. Relative entropy, Kullback-Leibler divergence. Another measure of the difference between two probability distributions. Not symmetric, KL, P, Q equals KL, Q, P. Differential entropy. The entropy of a continuous random variable, instead of a discrete one. Requires integration instead of summation. In summary, Shannon entropy is a fundamental concept in information theory that quantifies the amount of uncertainty or information associated with a random variable. It has broad applications in various fields, from data compression to machine learning, and provides a powerful tool for understanding and managing information. The key is to remember that higher entropy means more uncertainty and more information gained when the outcome is revealed.